Assalamualaikum and a very good morning to our panel. My supervisor Dr. Hasni Mulyati Tellurite, my co-supervisor Dr. Azuraida binti Ahmad, and to all my friends. My name is Nur Fatina binti Ramli, and today I'm going to present my review paper for this semester, which is the effect of thulium oxide on the structural properties of borate, tellurite, and borotellurite glass. My review paper consists of introduction, structural properties such as density, molar volume, Borate transform infrared FTIR spectroscopy, and SRD diffraction, SRD analysis, conclusion and reference. Introduction. First of all, what is glass? Glass is amorphous, hard, brittle, transparent or translucent supercooled liquid of infinite viscosity. According to American Society for Testing and Materials (STM), glass can be defined as an inorganic product of fusion which has been cooled to a rigid condition without crystallization. It possesses no sharp melting point, crystalline structure and definite structural formula. Today, glass are widely used in optical lens, prism, fine glassware, electrical transmission, laboratory glassware, etc. A glass has special properties not found in other engineering material. These properties are transparency and hardness at room temperature, sufficient strength and excellent corrosion resistant to most normal environment, good electrical insulator, and unaffected by air, water, acid, or chemical reagent. Next, we look at the properties of borate, tellurite, and borotellurite glass. Borate glass can classify as a network former because it can form glass on its own without mixing with other oxide. Research by Mahasberan et al. 2011 found that borate-based glass oxide has unique physical characteristics such as low melting point, high transparency, high photon energy, high thermal stability, and excellent rate at solubility. From the previous research by Hasni Mulyati et al. 2016 stated that tellurite glass can form glass when mixed with other alkaline earths, rare earth ion, or transitional metal oxide. According to Mahasberan and Marimutu 2012, the transitional metal oxide that is suitable to mix with tellurite glass is boron oxide, phosphate, and silicon dioxide. Besides that, tellurite glass has many unique physical characteristics like high dielectric constant, low melting point, excellent infrared transmission, and low processing temperature. Borotellurite glass can be divided into borate-based oxide and tellurite-based oxide, where both of these oxide has many properties that making it to have a wide range of technological purpose because they have a special structure like low photon energy, high thermal stability, high chemical durability, and easy to fabricate. Then we proceed to thulium oxide. According to research conducted by Gevavi 2009, thulium oxide are one of the rare earth metals that act as network modifier and reduce TE coordination. Thulium oxide is excellent thulium source with fine use in glass, optical, and ceramic applications. In this review paper, I will be concentrate on the effect of thulium oxide on the structural properties of borate, tellurite, and borotellurite glass. Density, molar volume, FTIR, and XRD analysis were examined in order to explore the structural properties of the glass. According to Dueda and Sadi 2009, the density is a powerful tool capable of exploring the change in the structure of glass and is affected by the structural softening or compactness. This statement was supported by Siddiq et al. 2013 and Hasni Mulyati et al. 2017. Reported by Azuraida et al. 2015, molar volume can be used as a parameter to identify an open structure that suggests value of molar volume corresponds to the maximum open structure. In borate glass, the density was increased and the molar volume was decreased with the increase in thulium doping level. The increase in the value density was attributed to the replacement of lighter atomic species by a heavier one. Conversely, the reduction in molar volume with the increased contents of thulium doping signified the enhancement of the glass compactness, so-called network shrinking. In tellurite glass, the density was increased with the increased thulium doping level, which was linked to the increasing number of bonds per unit volume. This means that the glass sample have less free volume. The molar volume decreased with the concentration of thulium oxide. This might be due to a reduction in the interatomic spacing and TeO bond length. In borotellurite glass, the density and molar volume were observed to be increased with the addition of thulium oxide. Molar volume also increased due to the large length of the bond and greater Thulium oxide coordination number, leading to a rust-free volume within the network of glass. The structure of the glass was studied extensively using the FTIR spectroscopic technique. The aim of this technique is to measure the absorption of infrared radiation by the sample material versus wave number and to identify molecular component and structure. The pure borate glass are made up of group trigonoplanar BO3 and tetrahedral BO4. According to Diaz et al. 2016, the first bend at 700 might be caused by the bending of BOB linkage. The asymmetric stretching relaxation of BO band of BO3 unit caused the group of band at 1200 until 1600, and the last band in the range 800 until 1200 caused by the BO bond stretching BO4 unit. In the article written by Ma'rif et al. 2019, the bending vibration of BOB linkage participating in the network of borate structure at 694 until 703. The stretching vibration mode of BO linkage appeared from BO3 unit at band 1352 until 1375, and stretching vibration of BO bond emerged from BO4 unit at band 1050 until 1055. Afterward, the characteristic of Thulium oxide structural unit can be divided into two spectral regions, which are trigonal pyramid TeO3 and trigonal bipyramid TeO4. According to Al-Khawkani et al. 2018, the band in the range 775 until 790 were assigned as a stretching vibration of TeO3. Next, the bands between 575 until 601 are caused by vibration of the continuous network made up of TeO4. Al-Khawkani et al. 2031 reported that the first band is around 732 until 798, caused by the stretching vibration of TeO3, and the second band from 536 until 588 were assigned by the vibration continuous network consisting of TeO4. Additionally, Borotellurite glass can be classified into two classes, which are borate oxide and tellurite oxide. According to article that written by Hasim Mulyati 2016, the peak allocated for BO3 appeared at 1200 until 1400. Next, the peak in the range 850 until 1100 are attributed to BO4 stretching mode of tetrahedral boron coordination, and the band in the range 600 until 640 are attributed as TeO4. This data also in agreement with their next research in 2017. From the previous table, it can be inferred that all the borate, tellurite, and borotellurite based glass with characterized using the FTIR spectroscopy method have slightly varied wave number, but are in the same range. Thus, TMO bond does not exist in borate, tellurite, and borotellurite glass, which might be owing to the low concentration of thulium that the equipment cannot be detected. X-ray diffraction XRD analysis is a method used in material science to evaluate the crystallographic structure of a sample. The absence of sharp crystalline peak in the XRD pattern indicates that the sample is entirely amorphous. In borate glass, the amorphous nature was demonstrated by complete absence of sharp crystalline peak and the existence of a massive halo. Moreover, reported by Al-Khawkani et al. 2031, there were no sharp peak in the XRD pattern of tellurite glass sample, just broad peak at a low angle, and the amorphous halo will verify the glass sample were amorphous nature since there were no indication of crystalline phase. Next, the absence of peak formed in the XRD pattern for borotellurite glass sample confirmed the amorphous nature of the sample. Conclusion. As conclusion, all the properties that I stated earlier are important and have their own characteristics. The properties of density and molar volume in borate and tellurite glass were inversely proportional. This means that as density increased, molar volume decreased and vice versa. This might be due to the size of particle for each glass composition, the compactness of the glass network, and the increasing number of non-bringing oxygen in the glass structure. Next, the properties of density and molar volume in borotellurite glass were directly proportional, which indicate the molar volume increased as density increased. The increase in molar volume was most likely affected by the development of free volume in glass sample. It can be inferred that all the borate, tellurite, and borotellurite glass investigated using the FTIR spectroscopy method have slightly varied wave number, but are in the same range. The SRD pattern of borate, tellurite, and borotellurite glass sample reveal no crystalline peak. It can be concluded that all the glass samples are amorphous nature. References. This is a few of references that have been used to complete my review paper. I think that's all from me. Thank you.